Hi all, welcome to my lecture series on subject wireless communication. My first video deals with evolution of communication, the ancient communication methods, types of communication wired and wireless, then the introduction for wireless communication, then history of communication and certain basic concepts in wireless communication like propagation, multipath propagation, the effects for it, the fading and propagation mechanisms in wireless communication, shadowing and path loss. In this lecture, I'm going to discuss about the propagation modes. A reliable propagation model is one which calculates the path loss with small standard deviation. This will help the network engineers and planners to optimize the size, coverage area, and to use the correct transmitted paths. Hence, prediction of path loss is an important element of a system designed in any communication system. In the radio and TV broadcast systems, the prediction of path loss is very important as the environment is constantly changing with time. A question arises in everyone's mind. What question is it? How to calculate the path loss with maximum accuracy? A solution to this problem is propagation model. This propagation model has been further classified into two types, or the prediction method has been classified into two types. One is empirical model and the next one is deterministic model. So what is empirical model? Here it involves the use of objective quantitative observation in a systematically controlled replicable situation in order to test or refine a theory. So what are we going to do here? You're just going to observe with all the things. And coming over for your deterministic, it deals with the mathematical formula for characterization of radio wave propagation as a function of frequency, distance and other conditions. So what I'm going to do in deterministic, you're just going to put a formula for all the waves. Well, actually what we want to do, we want to predict the path loss, right? So you're going to get the received signal. For the signal you're going to write some formulas, and with the help of the formulas you're going to predict the values. So that method is deterministic method. And the propagation, I already told you, propagation model is used to predict the average received signal strength at a given distance from the transmitter. And the propagation models has been further classified into two types. One is large scale fading, small scale fading. What do you mean by large scale fading? So when the user moves over a large distance, the average signal strength gradually decreases. This phenomenon is referred to as large scale fading. So large, now what is large? If the user is moving for a long distance, the average signal is decreases. So vice versa, right? For longer distance, decreases. Okay, this phenomenon is called as large scale fading. And what is small scale fading? So when the user moves over a short distance, the instantaneous received signal strength fluctuates rapidly, giving rise to small scale fading. Okay, here it is just the reverse and here it is going to be the reverse. Right? So this is the propagation model types. Then now going for the model, I'm going to take a free space model. What I'm going to do here, I'm going to transmit a signal from one end to the other end. I'm going to determine what is the power received in the signal. By what phenomenon? Free space model, right? So I'm framing the question as my aim is to predict the amount of signal that can be effectively received the receiver with the help of this free space model. Now for proving it, I'm going to consider a diagram. I'm going to take an antenna at the transmitter side and another antenna at the receiver side. Right? And both the antennas have been separated by a distance I've designated as small d. And I'm going to give the gain for the transmitting antenna to be GT and the power of the antenna to be PT. Next, the gain for the receiving antenna is designated as GR and power is designated as PR. Okay, so I've just and power is PR. Okay, and the parameters, whatever I stated just now, I've just put up here in the slide. Okay, let's move on. What is going to happen? So first, I'm going to look into the transmitter side. The power density of the transmitted signal is given by, can you remember the formula for power density? It is the power received divided by surface area. So let us put it in the formula or put it in denotions. So power density is equal to power received is PT divided by 4 pi d squared surface area. And we have to consider the gain of the transmitting antenna, right? So equation 1, I'm just going to consider the gain of the transmitting antenna in equation 1. So that it gets transformed into PD is equal to, I've just copied this equation as such and just putting a gain for the transmitting antenna. Next, coming over to the receiver side, right? The amount of power effectively received by the receiving antenna is decided by an effective aperture of an antenna. Okay, so what does this effective aperture stands for? It is nothing but power received divided by power density. Okay, let us put into equation effective aperture is equal to power received divided by power density. So let's move on. So power PR is equal to PD into AA. What have I done over here? So I'm just writing this equation. Which equation? This PD equation. I'm just writing it over here. Okay, so that is what is put up over here. PD into AE. So power received is equal to PD into AE. So I'm just putting it over here. Instead of the power equation, I'm putting it over here. Okay, next again. I'm just going to have a relationship. Consider a relationship between G and AE. It is given by the relationship so. So AE is equal to lambda square divided by 4 pi into G. Go substitute this AE in this equation. Right? What comes? I've just substituted and got like this. Okay, so it is something, look here, my 4 pi has been repeated over here and fully confusions over here. I'm just going to rewrite this equation, right? If I rewrite it, what becomes? The received power is equal to transmitted power into gain of the transmitting antenna into the gain of the receiving antenna into lambda square divided by 4 pi d squared into length. This L stands for the losses occurring. Okay, so this equation is designated as, or it is called as a free space equation. So by heart it once. So what is free space equation? Note it down. It is nothing but the received power is equal to PT GT GR lambda square divided by 4 pi d squared into L. Right? So again, so received power, I'm just formulating it once again. The received power is equal to, I've just copied the equation as such. Okay, and the parameters I'm just designated. So what is PRD? It is nothing but the received power, which is T2R separation by distance T. Then as stated already, PT is a transmitted power, GT is a transmitting antenna gain, GR is a receiving antenna gain, and D is a separation between the two antennas, transmitting antenna and the receiving antenna. L is a system loss factor whose value is greater than or equal to 1. And lambda, all know it is wavelength in meters. Right? So again, next what happens? I'm taking this free space equation into consideration, and you already know that the path loss is general is defined by the transmitted power by the received power. I'm just writing it as such in words. The words I'm putting it in a formula. Okay. So free space path loss is equal to the transmitted power divided by the received power. Right. So just now look here now. My PR is here. My PT is here. Okay, so what I'm going to do, I'm just going to bring this PT down. That is PR by PT is equal to, I've just written over the left out formulas. What if I bring this PT down, what are the left out terms? GT, GR, lambda squared divided by 4 pi d squared. Now I'm just not going to consider this loss, just leave it. Right? Okay, so finally I can tell you that I've written PR by PT is equal to so much. Now what I'm going to do, I'm just going to write the reverse of this. So this PT comes up and PR comes down. So just reverse it. PT by PR is equal to reverse of this side. So 4 pi d the whole square divided by GT GR lambda square. So you always consider your gain to be in decibels. Right? Path loss is always measured in decibel scale. So this is the path loss, the free space path loss. I don't want in this format, I want it in decibels. So what would it be? You should take logarithm of it. So my loss is equal to 10 log of PT by PR. So 10 log of, what is this PT by PR? I'm just substituting this equation over here. Right? Now again, what I've written here, I've denoted my path loss in decibels whose value is 10 log 4 pi d the whole square divided by GT GR into lambda square. Now what I'm going to do, I'm just going to transverse it. Okay, I'm just going to do the reciprocal inside this bracket. If I'm doing the reciprocal, what should I put? I should put a minus over here. So my path loss in decibel is equal to minus of 10 log. This I've just written this as reciprocal. That is why I get a minus sign over here. Now, assuming that the gains are unity. Gain. What is the gains? The transmitter gain and receiver gain is assumed as unity. So when you substitute for gains as unity, what is the balance remaining here? So path loss in decibel is equal to minus 10 log lambda by 4 pi d the whole square. The gains are considered as unity. Okay, so consider the far field of Fraunhofer region or Rayleigh distance. The far field of Fraunhofer region of a transmitting antenna is defined as the region beyond the far field distance, which is related to the largest linear dimension of a transmitted antenna aperture and the carrier wavelength. Then the Fraunhofer distance is expressed as, it is in equation 1 which was stated earlier. The far field region, the DF, the Fraunhofer distance, must satisfy the following conditions. That is, the Fraunhofer distance should be greater than capital D and the Fraunhofer distance should be greater than the lambda. The received power reference distance must be chosen such that it lies in the far field region. That is, D0 should be greater than or equal to DF. And D0 is chosen to be smaller than any practical distance used in mobile communication system. And the received power in free space, the distance greater than D0 is expressed as. So I'm getting my equation as PRD is equal to PR D0 into D0 by D the whole square, whose D0 lies in the D to DF. So for the large dynamic range of received power levels, the equation becomes, or it should be expressed in decibel dBm or dBWO. If PR is in units of dBm, the received power is. So the previous equation I'm writing in terms of BBM. That's it. So what is the equation? PR of D dBm is equal to 10 log PR D0 divided by 0.001 watt plus 20 log D0 by D between the D0 should lie in the limits of D to DF. Okay, so this is the received power. We have found out the received power using free space path loss model. Okay, this is all for this lecture. In the next lecture, we'll be discussing about Touré models. Kindly watch the videos. Thank you very much.